For over a century, physics has been built on two foundational pillars. On one side stands Einstein's theory of general relativity, a grand description of gravity that directs the cosmic ballet of planets, stars, and galaxies. On the other, we have quantum mechanics, the spectacularly successful, yet deeply strange, rulebook for the frenetic world of atoms and particles. Each theory is stunningly precise in its own realm. But here's the problem. The two are fundamentally incompatible. They speak different mathematical languages and describe two totally different realities. One is smooth, continuous, and predictable. The other is pixelated, chaotic, and ruled by chance. This is the deepest crack in our foundation of knowledge, the greatest unsolved mystery in all of science. But what if the key to uniting them isn't some new, exotic particle or a hidden dimension, but a secret architecture woven into reality itself? A geometric principle that's been staring us in the face all along. A simple, elegant twist. What if the fundamental blueprint for our cosmos looks uncannily like the blueprint for life itself? Hello everyone, my dad might not be able to see you all for a long time due to work. From now on, I'll be leading you all on a journey to explore secrets. Recording videos is not easy, so I hope all the uncles, aunts, brothers, and sisters will enjoy them. And I also hope you'll click the little bell. Section 1. The Two Titans. To really get a scale of this problem, we need to appreciate the two theories we're trying to unite. Let's start with the big general relativity. Einstein's masterpiece tells us that space and time aren't a static backdrop for the universe. They are a single dynamic fabric, space-time. Massive objects, like the sun, warp this fabric, and we experience that curvature as gravity. Planets orbit the sun not because of a mysterious pull, but because they are following the straightest possible path through the curved space-time the sun creates. It's an idea of profound geometric beauty, confirmed for over 100 years and essential for everything from your phone's GPS to understanding the mergers of black holes. It paints a picture of a universe that's smooth, continuous, and deterministic. Then we have the world of the very small, the realm of quantum mechanics. This theory describes a universe that's anything but smooth or predictable. Down at the subatomic level, reality becomes a frantic dance of probabilities. Particles can exist in multiple places at once, only snapping to a definite location when we measure them. Energy isn't continuous. It comes in discrete packets called quanta. This is the world of the standard model of particle physics, which classifies all the known fundamental particles, quarks, electrons, and bosons that carry forces. The Standard Model brilliantly describes three of the four fundamental forces: electromagnetism, the strong nuclear force holding atoms together, and the weak nuclear force governing radioactive decay. It's arguably the most successful scientific theory ever created. But you might notice one force I didn't mention: gravity. Section 2. The cracks in physics. And that's where the trouble begins. General relativity is our theory of gravity, but it's classical. It knows nothing about the bizarre rules of the quantum world. The Standard Model is our quantum rulebook, but it accounts for three forces and has no place for gravity. For most things in the universe, this isn't a problem. On the scale of planets, quantum effects are negligible. On the scale of atoms, gravity is so weak it's irrelevant. But this neat division breaks down in two extreme places: the singularity at the heart of a black hole and the singularity at the very beginning of time, the Big Bang. A singularity is a point where our theories predict that physical quantities, like density, become infinite. Inside a black hole, a massive star collapses to a point of supposedly zero volume and infinite density. In the Big Bang, the entire universe is thought to have begun from a similar state. At these points, the immense gravity demands general relativity, but the infinitesimally small scale demands quantum mechanics. And when you try to use both sets of equations, they fail. They spit out mathematical nonsense, like infinite probabilities, which tells us one thing: our theories are incomplete. They're a giant signpost that says, beyond this point, new physics required. This conflict runs even deeper, down to the very nature of time itself, is what physicists call the problem of time. In quantum mechanics, time is absolute, a universal clock ticking forward for everything. But in general relativity, time is relative. It can be stretched by gravity and warped by motion. So, how can you build a single theory of everything when your two best theories can't even agree on what one is? Section 3: The Search for a Bridge. For decades, the mission to find a theory of quantum gravity has been the holy grail of physics. This quest has produced two main frontrunners: string theory and loop quantum gravity. String theory's big idea is that fundamental particles aren't points, but tiny vibrating one-dimensional strings. Just as a guitar, strings vibrations create different notes. The different ways these strings vibrate create all the particles and forces we see. One specific vibration would even produce the graviton, the hypothetical quantum particle of gravity. The catch: string theory requires a universe with at least 10 or 11 dimensions, many more than the four we perceive. After decades of work, it has yet to produce a single testable prediction. Loop quantum gravity takes a different path. Instead of adding new things like strings, it tries to quantize spacetime itself. It proposes that the fabric of space isn't continuous but is woven from discrete, indivisible loops at the unimaginably tiny Planck scale. Spacetime becomes a kind of quantum network. This avoids some of string theory's issues, but it too has struggled to make predictions we can test with experiments. Both are monumental intellectual achievements, but the final, unifying theory remains out of reach. Section 4: The Bridge to the New Idea. So what if the answer isn't in new particles or extra dimensions? What if the solution lies not in new times things asterisk, but in a new times principle asterisk? A hidden geometry woven into reality itself? What if the universe, at its root, follows an architectural rule that is both profoundly simple and startlingly familiar? What if the code of the cosmos is a helix? We know the double helix as the blueprint of life, the twisted ladder of DNA that carries the instructions for every living thing. It's a structure that masterfully combines simplicity and complexity. What if nature uses this same geometric principle, not just for biology, but for physics itself? Section 5: Introducing a New Theory. This brings us to a bold new idea that emerged in 2025 from a peer-reviewed paper in the Journal of High Energy Physics. The theory, developed by mathematician Robert Mongeau and called colored gravity, proposes a radical new framework for uniting physics. To be clear, this is a very new theory. While it has passed the bar of peer review, it is not yet mainstream and still awaits the experimental proof needed to challenge established models. But its central idea is captivating. It suggests that spacetime itself is not just curved, but has an intrinsic twist, forming a colored fabric that behaves like a twisted double helix, remarkably similar to DNA. The color here doesn't refer to visible light, but to the color charge that describes the interactions of quarks in quantum physics. The theory proposes that this hidden helical geometry could be the key to finally uniting gravity with the other forces of nature. Section 6: The Core Explanation. How could a twist in spacetime explain our universe? The colored gravity theory builds on several profound, if mind-bending, pillars of modern physics. First, it takes inspiration from Sir Roger Penrose's twistor theory, which dates back to the 1960s. Twistor theory reimagines reality, suggesting that the fundamental objects aren't points in spacetime, but light rays, or more abstractly, twistors. Spacetime, in this view, is a secondary property that emerges from the relationships between these twistors. Second, it draws on a stunning discovery from 1995 by physicist Ted Jacobson. Jacobson showed that Einstein's equations, the very laws of gravity, can be derived from the laws of thermodynamics. This suggested gravity might not be a fundamental force at all, but an emergent phenomenon like temperature or pressure arising from the behavior of deeper microscopic components of spacetime. Mongeau's colored gravity theory attempts to weave these threads together. It proposes that reality is fundamentally built from a complex geometry described by a mathematical group called U1. 3. The true innovation is the claim that this underlying structure gives spacetime a double helix twist. From this single geometric premise, the theory attempts to unify gravity with the forces of the Standard Model. Remarkably, it offers precise predictions for things like the Weinberg angle, a key parameter that governs how the electromagnetic and weak forces mix. It even predicts subtle differences in these interactions for quarks versus other particles, which is consistent with experimental results from places like CERN. Section 7. The implications if, and it is a big if, a theory like this proves correct. The consequences would be profound. The seemingly arbitrary collection of particles and forces in the Standard Model would suddenly snap into focus as a logical outcome of a single, elegant geometric principle. The universe wouldn't just times have times these laws, it would be times built times from them. This helical structure could also give us a new way to understand singularities. Instead of a point where space-time breaks, a singularity might be a region where this helical geometry becomes infinitely compressed. The beginning of the universe might not be a point in time, but an atemporal geometry from which our expanding cosmos emerged. For black holes, the famous information paradox, the question of what happens to information that falls in, could be reframed. Perhaps the information isn't destroyed, but is encoded in the twist of the singularity's helical structure, preserved in a way we don't yet understand. It paints a picture of a universe that is, from top to bottom, a single unified geometric object. Section 8. The caveats and future. Now, let's come back to Earth. It's essential to repeat that colored gravity is a new and unproven idea. While it has been published in a prestigious physics journal, it is still in its infancy. It has not yet faced the intense scrutiny and experimental testing that any new theory must survive to be accepted. Its claims are extraordinary, and extraordinary claims require extraordinary evidence. Physicists will rightly demand testable predictions. Can this theory explain the mysteries of dark matter and dark energy, which make up 95% of the cosmos? Can it predict the mass of a new particle? These are the immense hurdles any new theory of everything must clear. However, the value of an idea like this isn't just in being right, it's in its power to provoke new questions and force us to reconsider old assumptions. Could the answer to physics' deepest problem really be geometric? Could the uncanny parallel between the blueprint for life and the blueprint of the cosmos be more than a coincidence? It's a powerful reminder that even after a century of being stuck, there are still new ways to imagine the universe. The quest for a theory of everything is one of the greatest intellectual adventures in human history, pushing the boundaries of both knowledge and imagination. If you enjoy exploring these frontiers of science, subscribe for more journeys into the unknown. And let us know in the comments, what do you believe reality is truly made of? From Einstein's smooth space-time to the chaotic dance of quanta, we have been searching for a single coherent story of our universe. We've imagined it made of points, of strings, and of loops. Now, we're invited to imagine a universe built on one of the most elegant principles we know, a simple twist. The idea of a helical cosmos, where the laws of nature are encoded in a structure reminiscent of life's own blueprint, is a profoundly beautiful one. While this theory remains a speculative dream, it embodies the spirit of scientific inquiry to look at our vast, complex universe and believe that underneath it all lies a simple, elegant, and understandable truth. Whether the final answer is a helix, a string, or something we can't yet imagine, the search itself is what matters. It's a testament to our unending desire to not just exist in the universe, but to understand it.